In this video, I'll show you how the Meyboom method allows us to determine groundwater recharge using stream hydrographs. So we have some basic water budget questions. Including how much of the precipitation actually infiltrates. And just how much groundwater gets into the aquifer every year. So we want to determine annual groundwater recharge. So we'll answer these questions by quantifying aquifer discharge. So here's the idea. We have stream base flow. And remember, base flow is the water coming out of the aquifer to supply the flow in the stream during periods when there's no overland flow. So the stream base flow is equal to aquifer discharge. And aquifer discharge is going to be equal to the aquifer recharge. So you see there's a direct connection here between amount of water that recharges an aquifer and the amount of water that comes out in the base flow. And this equality is true if there is no change in storage and you have basic hydrologic equation, conservation of water. What goes in comes out. And if you measure what comes out, then you have a measure of what actually infiltrated in the first place. So the quantification is closed at this point. We have amount in and amount out, and by measuring amount out, we'll determine what goes in. Okay, I'm going to erase this page and go on to a clean sheet. So, in the Meyboom method, the basic idea is that precipitation is seasonal and that stream base flow decreases over the course of the dry season. Now, this idea of seasonal rain and seasonal dry is true in many areas of the world, including the Northwest. So what do you expect to see if we plot the stream hydrograph data, not Q naught, the flow, and Q versus time? What we see is that there's a buildup of stream flow during the rainy season, and then a decay of the stream flow during the dry season, and then a buildup during the next wet season, and a decay during the dry season, and so on from year to year. So this period between the beginning of the buildup of the stream flow and the point at which stream flow is minimum again, there's that time. This is the water year. It's not the calendar year, it's the water year. And a typical water year starts over here at minimum stream flow around October 1st. Then into the fall and early winter we have the buildup of the stream as all the heavy precipitation occurs. Then in late spring through the summer we have the decay of the stream flow to the end of the water year. So here's one water year, 2 water years, 3 water years. The period from the maximum flow down to the minimum flow during a time in which there's very little precipitation is the period of the base flow recession. Okay. So this idea of buildup from precipitation and decay from base flow is obviously a useful idea, except for some of the northwest streams that are fed by glaciers or by permanent snowfields. So you would not want to apply this method in those cases. If you want to look at the basic concept here, we imagine here's a valley, here's a stream running through the valley. So we have the stream flowing down that way. We have hill slopes sloping down to the stream. We have water coming in the form of rain. Here some of it infiltrates. There is a water table somewhere down here, and within the aquifer then the water is flowing and eventually ends up flowing and discharging into the stream. So during the rainy season, the level of the aquifer rises a bit, and during periods of no precipitation, the level of the aquifer can decrease as water drains out of the aquifer and into the stream. So it's an observation, here's the hydrograph up here, that during base flow recession, this curve is exponential. It goes, decreases, decreases, and this exponential curve can be represented mathematically with Q. The flow is equal to some initial flow value, Q naught, times exponential of minus T divided by tau. I'm going to use a little e there to remind myself that this is the base natural e time constant, because we're using the exponent here. Okay, so base flow proportional to the amount of water in the reservoir. More water, more base flow, less water in the aquifer, less base flow, comes out mathematically as an equation of this kind of form. Okay, so this exponential decay here is the base flow recession. Okay, and let's just look at what this equation kind of tells us. Well, if we have some value here, this value is going to decrease, and after a time interval tau sub e, after one time constant, the amount of flow, we come across that amount of time and we come down, is going to be down by minus t over tau. So if t is equal to tau, then this is minus 1, so it's the exponent of minus 1, and exponent of minus 1 is 0.368. So after one time constant, the flow is down to 0.368 of its initial flow. After two time constants, it would be exponent of minus 2, and so forth. Okay, why do we use these equations? Well, to begin with, the form of the recession suggests that an exponential is a good choice, and the concept of having the amount of flow proportional to the amount available also suggests an exponential kind of equation. Furthermore, exponential equations have nice properties, and I'll go on and wipe this page and point out that whenever you have an exponential curve, this curve keeps on getting smaller, fractionally decreasing, closer and closer to 0, but never quite getting to 0. even though it never quite gets to 0, the area under this curve is well defined. And the area under that curve, well, Q, that's volume of water per unit time. So for instance, it'd be meters cubed per second. Meters cubed per second per time, that's the area under here. That's going to give us, that area is going to be the volume of water in the aquifer. And the area going from Q naught, the initial discharge, all the way out to T equals infinity, that's going to be the total amount of water available in the aquifer. So here's where our exponential equation becomes useful. The total water is going to be equal to an integral from the initial time, 0, to time infinite, letting the water totally drain out of the aquifer at infinite time, of the flow times dt. Now this equation, we substitute in our exponential, so we have Q naught, integral from 0 to infinity of exponential of minus t over tau sub e dt. And we look up, or we remember how to take the integral of an exponential, and it turns out that we pull out a factor of minus 1 over tau e, and that gives us minus Q naught tau e and times the exponential of minus t over tau e evaluated from 0 to infinity. So that means we substitute in 0 and we substitute in infinity. Now notice, if you substitute in infinity, you're taking the exponential of minus infinity. Exponential of minus infinity is 0. The exponential of 0 is 1. So that's very simple. 0 and 1 are our two limits, and we plug those in, and in fact the final answer is Q naught tau e. So if we know what the time constant is, in other words, how fast this curve is decaying, and if we know what the initial value of flow is, the product of the two gives us the total amount of water available in the aquifer. So, amount of water can be quantified if you measure base flow and determine the recessional time constant, tau sub e. Fantastic. Okay, let's work through how we are going to do this. So first question, how do you measure tau e? Now we can do that with two measurements of the base flow. So if we have a curve of the form exponential, and we have a Q1 here and a Q2 here, and if we made this measurement at time 0 and this measurement at time t, then we just use our equation, which says that Q2 is equal to Q1 exponential of minus t over tau e. Okay, so we rewrite that as Q2 over Q1 is equal to exponential of minus t over tau e. Take the log of this. We're going to take the natural log. I'll put ln there. So we have natural log ln of q2 over q1, and the natural log of the exponent is just minus t over tau e, and that gives us the answer then. Tau e is equal to minus t divided by the natural log of the ratio of the discharges. Bingo! Okay, let's take some examples. What if Q1 is 3,500 cubic meters a second, Q2 is 1,500 cubic meters a second, and the time it took to go from a flow of 3,500 meters to 1,500 meters was 100 days. Okay, so we have tau e is equal to 100 days divided by natural log of 3,500 over 1,500. Plug that into our equation, into our calculator, and we're going to come up with 118 days. Now notice, I've kept 3 significant figures in this calculation. I've rounded to the nearest day. This kind of makes sense in this equation. You notice we've got 2 significant figures in our stream flow, and it looks like 1 significant figure in our count of days, but I think that you could argue that days are pretty easy to count, so we probably know this number to 3 significant figures, the number of days that it took to decay. Both of these numbers, the stream flow, it's unlikely that our hydrograph is going to be more accurate than, say, 10%. So 2 significant figures is okay in here. So it may be that our time constant is really only 2 significant figures, but I'll give you credit for 3 significant figures if you were to do the calculation. I think it's worth keeping 3 significant figures. Now, at this point, I'll pose the question, and you can test yourself whether you understand what we've done so far. And the question is, what is the base flow from this stream given these numbers of discharge and time constant, and calculate it yourself. What is the base flow after 150 days? If you can do that, and if you can get the right answer, then you're understanding what we're doing so far. So let's move on now. I'm going to wipe the page and start fresh. So here's the basic idea. If base flow is exponential, then a plot of the log of discharge versus time is going to be linear. Okay, so let's show a linear plot of log versus time. So I draw my axes again. Now instead of drawing a linear scale, I'll draw a log scale. And let's go from 1 to 10 to 100. So there's a log scale. This happens to be a base 10 log rather than the natural logs that we've been doing so far. And now I put some time intervals on here. 0, 1, 2, 3. And I'm going to draw a straight line. Okay, so any exponential curve will plot as a straight line. And so this is one way of determining that our base flow is exponential, is plotting it on a log plot. And if you see it showing up as a straight line, then you know you have a exponential decay. Now, we can determine very easily on this base 10 log plot a time constant, the time constant associated with dropping by an order of magnitude in flow. So if we go from 100 down to 10, we need to know how long that takes. And on this scale, it looks like, say, about 1.3 time units. This could be months for all we know. Anyway, there's a time constant here, which I'm now going to call the base 10 time constant. So remember, before I had a little e for the exponential time constant. Now I have a base 10 time constant. Okay, what's the relationship between base 10 time constants and natural log time constants? Well, go review your math, but tau 10 is equal to tau e times the natural log of 10, and that's going to be tau e times 2.3026, which for most of our calculations can be just simply rounded off to 2.303. That gives us 4 significant figures, and there's very unlikely to be examples in which we need to know the answer to more than 4 significant figures. So the base 10 time constant is 2.3 times larger than the natural log time constant. Okay, why use base 10? Well, it's easy. We can get log, semi-log plot to plot our data on. Furthermore, if we know our base 10 time constant, we can write that the flow is going to be equal to the initial flow, Q naught, times 10 raised to the minus t over the base 10 time constant, tau sub 10, which is related, as we wrote up here, to the natural log, which would be QE, our Q naught, 10 to the minus t, and we substitute in over tau e times 2.303. Okay, so for every unit of time equal to tau 10, the flow in the stream drops by an order of magnitude. Now remember, we had formula for the amount of water in the aquifer, so V total, the total aquifer volume, is going to be equal to Q naught times tau E, the exponential time constant, but I can substitute in Q naught tau base 10 divided by 2.303. So this gives us the total available water at time 0 in our aquifer simply by plugging in the discharge, the base flow discharge, Q naught, and multiplying that by the base 10 time constant, dividing by 2.3. Now the remaining water after some time, V remaining, is going to be equal to the total water available times 10 to the minus t over the base 10 time constant. So if you weight one time constant, t over tau would be 1. 10 to the minus 1 is 0.1. You would have 1/10 of the total remaining after one time constant. Okay, let's plug in our previous numbers. We had, if you remember, Q naught was 3,500 cubic meters a second. Tau E was 118 days. So how much water was there in this aquifer? Well, V total is equal to 3,500 times 118. Okay, oops, now we have a problem. Oh, and we divide that by 2 point, oh no, that's the right number. I don't divide by 2.3. Okay, but 3,500 is in cubic meters per second, and we're multiplying that by days. So we need to turn days into seconds. So there are 60 seconds in a minute, there are 60 minutes in an hour, and there are 24 hours in a day. So at this point then I have converted 118 days into seconds and multiplied that seconds times 3,500. Plug that into your calculator and we're going to get 3.57 times 10 to the 10th cubic meters. So there's 35 billion cubic meters of water in this aquifer at the moment the recession began. Now what? Let's wipe the page, and we're ready to begin. We are ready to calculate the annual recharge from the base flow. Okay, starting point now is that we need stream hydrograph that extends over at least 2 years or more. So here's Q versus time. And here we go up during the recharge of the aquifer. Here the aquifer goes down during the, oh, and this is a base 10 plot here. So our recession looks linear. It recesses, then there's recharge, the base flow recesses, and there's recharge, base flow recession, recharge, base flow recession. So we see, looking at this plot, that during, well, first of all, how many water years do we have here? We have 1, we have another water year there, a third water year, and a fourth water year. So we've got 4 water years represented. Remember, we need at least 2 in order to calculate any recharge. Why is that? Well, at the beginning of the first water year recession, we have a Q naught, and from this recession we can get a tau sub E. So Q naught times tau sub E is going to give us the amount of water in the reservoir at this point. But we don't know how much of this water in the aquifer came from recharge and how much water was there at the beginning of the wet season. But now, if we know how much water is at this point, we can figure out how much water is left, V remaining, at the end of the recession. Then we have another recharge, and we have Q naught for the second water year. And if it's the same aquifer, the recessional time constant is going to be the same. So we only need to measure it once, or take the average of the slopes of these various years. And we can determine what V total is at the beginning of the second year. So the V total here at the beginning of the second year has some amount of recharge and some amount that was in the aquifer prior to recharge. The amount of recharge is going to be, so let's call it recharge, V recharge, is going to be equal to the V total minus the V that remained from the previous year. So it's the difference between the remaining water and the total water that is the amount that was recharged. Thus, for the first water year, we determine a remaining amount of water at the end of the water year. At the beginning of the second water year, we can then determine how much recharge occurred to get it to this point. Then we can calculate the amount of water remaining here and calculate the amount of recharge for the third water year and amount of water recharge for the fourth water year. So let's work it through. Let's take some examples. Let's assume that right here the flow was 95 meters cubed per second. The time constants, let's use a base 10 time constant, nice round number, 100 days. So the amount of water at the beginning of the first water year, V total, is equal to 95 meters per second, meters cubed per second, times 100 days, times 60, times 60, times 24, is equal to 3.56 times 10 to the 8th cubic meters of water. Now let's assume here that we made the measurement of how long the recession occurred, and let's say the recession extended over 200 days. So V remaining is going to be equal to V total times 10 to the minus T over tau base 10. If tau is 100 days, let's see. Oh, we need to be a little bit careful. I forgot to divide my 100 days base 10 by 2.303, and I actually did it to get this number. So there, if you were following along and plugging into your calculator, 95 times 100 times 60 times 60 times 24 divided 2.303 should equal 3.56. Okay, V remaining is going to be the total times 10 raised to the minus T over tau. T in this case is 200 days. Tau is 100 days, so that's 200 divided by 100. That's 2. 10 to the minus 2 is 0.01, or 1%. So the remaining water is going to be 3.56 times 10 to the 6th cubic meters. Well, let's put this in the same exponent as up there. So that's going to be 0.036 times 10 to the 8th meters cubed. Okay, so we started with 356 million cubic meters, and we ended up with 1% of that at the end of the season. Okay, now at the beginning of the new second year, this number is higher. Let's say that the number here is 130 meters cubed per second. So the discharge at the beginning of the next water year is higher than the prior water year. What does that mean? It means that there was enough recharge to put more water in the aquifer so that the initial discharge at the beginning of the recession was larger than the previous year. So the total water in the aquifer at the beginning of the second water year will be 130 divided by 2.303. I remembered to divide by my conversion factor there, times 100. It's still the same decay rate, times 60 times 60 times 24, and that number is going to be 4.88 times 10 to the 8th cubic meters. So at the beginning of the second water year, we have 4.88 times 10 to the 8th cubic meters. We know that we have more water because we had more discharge, but not all of this water here is from recharge because there was some water remaining in the prior year. So recharge will be 4.88 times 10 to the 8th minus what was there to begin with, and it's 0.036. Well, I'm just going to round it off to 0.04 minus 0.04 times 10 to the 8th. That's just consistent with our 3 significant figures in our calculation, which says then that the recharge between year 1 and year 2 is 4.8 times 10 to the 8th cubic meters of water. Okay, that's it. The Meyboom method allowed us to figure out just what the size of our aquifer was and to determine how much of the precipitation infiltrated to recharge the aquifer on an annual basis. And we could carry out this calculation then for years 3 and 4, and we could plot eventually the amount of recharge year by year. And if we know the surface area of our watershed associated with this aquifer, we could calculate how much of the rain made it into the aquifer.